Let's look at a chi-square goodness of fit test. We know how to test whether a sample proportion fits a hypothesis population proportion. But what if an outcome does not fall into only two categories, like win-loss, hit-miss, success-failure? When we have more than two outcomes, we use a chi-square goodness of fit test to compare the observed outcomes to the expected outcomes. For example, in large sets of data, the leading digit, the first digit of the data, is usually not uniformly distributed from 1 to 9, but instead often follows Benford's law. Here is the probability that the leading digit will be this digit. The probability, if you have this set of data, that the leading digit is 1 is 0.309. The probability that the leading digit is 2 is 0.176, etc. Regardless of the unit of measure, the lengths of rivers, the heights of buildings, population of cities, check amounts tend to follow Benford's law. When working for the Brooklyn District Attorney, investigator Robert Burton analyzed the leading digits of the amounts from 784 checks issued by 7 suspect companies. The frequencies of the leading digits 1 through 9 were found to be 0, 15, 076, 479, 183, 823, 0. If the observed frequencies are substantially different from the frequencies expected with Benford's law, the check amounts appear to result from fraud. Test the hypothesis that the check amounts do not fit Benford's law. Okay, find null and alternative hypotheses. The null hypothesis is that there's no difference. The stated frequencies are correct. The alternative hypothesis is that there's a change. There is a difference. Not all of the stated frequencies are correct. Okay, here are the stated frequencies. H sub 0 is P1 is 0.309, P2 is 0.176. This is the probability that 1 is the first digit. This is the probability that 2 is the first digit, etc. The alternative hypothesis is that not all of the stated frequencies are correct. Okay, we want to do a chi-square goodness of fit test. Do the data satisfy the required conditions? Here they are. Counted data condition. The data are given as counts, not measurements or percentages. So it can't be feet or pounds or something like that. They have to be counts. Independence assumption. Each subject that is counted is independent of the other subjects. Expected cell frequency condition. The expected values for each cell are all at least 5. Okay, calculate the test statistic. Here it is, kind of scary formula. Chi-square, I know it looks like an x square, but it's not an x square. Instead, it's the Greek letter chi. So we say chi-square. And don't say chi, it's chi. Chi-square is the sum of observed frequencies minus expected frequencies squared over expected frequency. So in this case, leading digit 1 through 9. Let's look at the observed. Okay, the observed, this is what we had for the observed. So those will go 0, 15, 0, 76, etc. As for the expected, these were the expected probabilities, the expected proportions. Oh, but don't say that there. Don't say, well, the observed was, for leading digit of 1, the observed was 0, and the expected was 0.309. No, that's wrong. No, what needs to go there is the expected frequency, not the expected proportion or expected probability, but the expected frequency. Now, if you have 784 checks, and this is the proportion that you expect to have leading digit 1, then when you multiply those together, you would expect 242 of the checks to begin with a 1. In the same way, if that's the probability that a check begins with a 2, and that's the total number of checks, this is the number of checks you'd expect to begin with a 2. And so these are the expected frequencies, okay? So let's go ahead and calculate our chi-square test statistic. Again, it's observed minus expected, all squared, over expected, and you sum those up. For example, this first one, observed is 0, expected is 242. Square that difference and divide by 242. 15 minus 138 squared over 138. 0 minus 98 squared over 98. 76 minus 76 squared over 76. We can do that one in our heads, etc. When you total all of these up, you end up with 3646.8. Is there a way to find the test statistic chi-squared on a graphing calculator? Because some of you out there are just dying. Well, we can't do this directly on the TI-83, sadly. Later calculators like the TI-84 can do the entire test. Here's the best way you can do it on a TI-83. You press Stat and then Edit, and then Observed. You enter the observed data in L1. You enter the expected in L2. You go to the top of L3 and enter, L1 minus L2 squared over L2 at the top of L3. Press quit, and then sum of L3. Sum is available under list math. I'll show you an example of what this looks like. Okay, so there's our table. Okay, so let's see how we get to our table. Again, we press stat and then edit, and that's L1. That's where the observed go. So we want 0, enter, 15, enter, 0, enter, 76, enter, 62, enter, 53, enter, 45, enter, 40, enter, 36, enter. Okay, so now we have our data entered in there, and we quit. Oh, I'm sorry, don't quit yet. Don't quit yet. We go to the top of L3, not to that first entry, but all the way to the top. This is so cool. So again, we're going to enter left parenthesis L1, that's second and then 1, minus L2, that's second and then 2. Close the parenthesis, square it, and then divide by L2. Enter. Oh, that is so cool. So this column will give us L1 minus L2 squared over L2. And that's what we got when we did it by hand, much more slowly. Okay, for the TI-84, here's what you do. You would just go to under stats and then test, you would choose chi-square goodness of fit test. The degrees of freedom is the number of categories minus 1, which in this case is 8. And then you just calculate. Oh, if you have that calculator, I'm envious. Okay, determine whether we should reject or fail to reject the null hypothesis uses a 0.01 level of significance, because we want to be really, really sure. None of this 0.05 stuff. It's got to be 0.01. We don't want to haul people before a court unless we're pretty certain. Okay, the rejection region is chi-square is greater than chi-square star, where chi-square star, that critical value, is from the table at the back of the book. Chi-square tests are always one-sided tests. Okay, so let's look at the chi-square distribution table. It's the 5th table in the appendix of our textbook, or you can just enter chi-square table into a search engine. Here's what it's going to look like. So in this case, the column we want is 0.01, and that's our significance level. And our row is going to be the degrees of freedom, which is n minus 1, number of categories minus 1. We have 9 categories, so 9 categories minus 1 is 8 degrees of freedom. That's 20.090. That's chi-square star. So that's our critical value of chi-square. So in this case, chi-square, our value, our test statistic is greater than chi-square star, the critical value. So we conclude that the null hypothesis is false. We reject the null hypothesis. Not all the stated frequencies are correct. This indicates that the checks may be fraudulent. Okay, find the p-value. Well, we want the area to the right of chi-square equals 3646.8. Here's what the chi-square distribution looks like with 8 degrees of freedom. To do this, we would just enter chi-square CDF. Chi-square, like the other ones, is available on your calculator under dister. So you can get that under dister. Okay, chi-square CDF. So this is the left endpoint, the right endpoint. So we would enter the left endpoint, 3646.8. That's the left endpoint. It's pretty far out there, 3646.8. The right endpoint is infinity, but your calculator doesn't have an infinity button, so we'll just enter 1 with a lot of zeros after it. That's 100,000. And then the degrees of freedom in this case is 8. And when we enter that, we get 0. That is our p-value. If the p is low, the null must go. So we reject H0. There is very strong evidence, and I mean very, 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 very strong evidence to conclude that not all the stated frequencies are correct. So we suspect fraud. Which values are most likely to have incorrect frequencies? Well, what we would do is look at the standardized residual for each term. It's observed minus expected over the square root of expected. Note that this is plus or minus the square root of that term that we summed up earlier. Those were the terms that we summed up when we calculated chi-square. Okay, so the first standardized residual will be the observed, which was 0, minus the expected, which was 242, over the square root of expected, which is square root of 242. Okay, there's a quicker way to do this. You can press stat, edit, and then you go to the top of L3. You can just enter L1 minus L2 over square root of L2 at the top of L3, and then enter. Here's what we end up with. So it's basically like what we did earlier, except instead of entering L1 minus L2 squared over L2, we just enter that at the top of L3. These are the standardized residuals, and so these are the ones that stand out. Those are the ones that are really pretty far from 0. Okay, a positive residual means the observed is larger than expected. A negative residual means it's smaller than expected. So for 5 and 6, the observed was much larger than we expected. And for 1, and to a lesser extent 2 and 3, the observed was much smaller than expected. Okay, and that seems reasonable because for 5 and 6, this is what we observed, and that's what we expected. For 1, 2, and 3, that's what we observed, and that's what we expected. So we suspect fraud.